November 8, 2024, European Space Agency's Sentinel-1 satellite completed its routine pass over Yellowstone National Park, transmitting radar data to ground stations in Norway and Alaska. Within hours, automated processing algorithms at the Nevada Geodetic Laboratory flagged an anomaly in the latest interferogram, the rainbow-colored image created by comparing two radar acquisitions separated by 12 days. The pattern was unmistakable, concentric bands of color centered on Yellowstone's Mallard Lake Resurgent Dome, each band representing 2.8 centimeters of vertical ground displacement. In less than 2 weeks, a section of Yellowstone's caldera floor had risen by nearly 20 centimeters. INSAR interferometric synthetic aperture radar is a space-based geodetic technique that measures ground deformation with centimeter precision. Unlike GPS stations positioned at specific points, INSAR maps deformation across entire landscapes, detecting movement invisible to the naked eye. The technology has revolutionized volcano monitoring, revealing that volcanic systems breathe, bulge, and subside on timescales from days to decades. But 20 centimeters in 12 days at Yellowstone? That was extraordinary. The last time deformation rates approached this magnitude was 2004 to 2009, when the caldera rose 18 centimeters over 5 years. This was 60 times faster. By November 9th, scientists at the Yellowstone Volcano Observatory cross-referenced the satellite data with GPS networks. Confirmation came quickly. 14 GPS stations across the caldera showed synchronized uplift matching the INSAR pattern. Station NRWY on the north rim of Mallard Lake Dome recorded 18.7 centimeters of vertical displacement. Station LKWY southwest of the dome, 16.3 centimeters. The deformation was real, coherent, and centered on one of Yellowstone's two resurgent dome areas where the caldera floor has been rising episodically since the last supereruption 640,000 years ago. Yellowstone is not a static geological feature, it's a living system in constant motion. Since continuous GPS monitoring began in the 1990s, scientists have documented multiple uplift and subsidence episodes. The caldera floor rises when magma, hydrothermal fluids, or gas accumulate at depth, pressurizing rock formations above. It subsides when pressure is released through fractures, gas escapes, or fluids migrate laterally. Between 2004-2009, Norris Geyser Basin rose 18 centimeters, the fastest documented uplift at the time. Between 2010-13, it subsided 14 centimeters. This cyclical breathing is normal for calderas. What's abnormal is the rate. The November 2024 uplift focused on Mallard Lake Dome, a 250 square kilometer area in Yellowstone's western caldera. This dome, along with its counterpart, Sour Creek Dome to the east, represents areas where the caldera floor rises above surrounding terrain, legacy features from post-collapse resurgence that began hundreds of thousands of years ago. Beneath Mallard Lake Dome, geophysical surveys map a complex hydrothermal system overlying the magma reservoir. The question facing scientists was the rapid uplift driven by magma intrusion from the chamber 8 kilometers below, or by superheated fluids pressurizing shallower rock. Sentinel-1, launched by the European Space Agency, carries a C-band synthetic aperture radar that images Earth's surface regardless of weather or sunlight. Every 12 days it passes over Yellowstone, transmitting radar pulses and measuring the return signal's phase. By comparing the phase difference between two acquisitions, scientists calculate ground displacement. The technique is so precise that it detects movements smaller than the radar wavelength, 5.6 centimeters for Sentinel-1's C-band. When combined with GPS, which provides absolute position, and tilt meters, which measure surface slope, INSAR completes a multi-sensor geodetic network that captures deformation in 3 dimensions with unprecedented resolution. The November 8th interferogram captured deformation from October 27th to November 8th. By November 15th, the next Sentinel-1 acquisition revealed continued uplift, an additional 12 centimeters between November 8th and November 20th. Cumulative uplift over 24 days, 32 centimeters. GPS networks confirmed the acceleration. More alarming, the deformation pattern was expanding. Initially confined to a 15-kilometer radius around Mallard Lake, by mid-November the uplift extended to 22 kilometers, encompassing parts of Midway Geyser Basin and approaching the Lower Geyser Basin complex. Seismic networks detected what geodesy measured. Between November 5th and November 20th, over 200 earthquakes rattled beneath Mallard Lake Dome. Most were of small magnitude 1.0 to 2.5, but their spatial pattern was telling. Hypocenters clustered between 5 and 8 kilometers depth, forming a vertical column directly beneath the maximum uplift zone. The earthquakes represented rock fracturing under stress as something pushed upward from below. Whether that something was basaltic magma intruding from the deep reservoir, or superheated water flashing to steam and overpressurizing confined aquifers remain the critical unknown. Thermal infrared satellites detected increased heat flux across Mallard Lake Dome. Areas that typically registered 30 to 40 degrees due to geothermal background heat now showed temperatures of 55 to 65 degrees. New steam vents opened near Firehole River, creating hazards for boardwalk visitors who reported the ground too hot to touch. Gas monitoring measured sulfur dioxide emissions rising from baseline 100 tons per day across Yellowstone to 280 tons per day by November 18th, with concentrations highest in the Mallard Lake area. SOI2 originates from magma degassing. Its increase suggested either enhanced permeability, allowing deeper gases to escape, or fresh magmatic contribution. Geodesists use mathematical models to invert deformation data, essentially running measurements backwards to determine the source depth, volume, and pressure change causing surface uplift. Applying these models to Yellowstone's November data, scientists calculated a pressure source at approximately 6 kilometers depth beneath Mallard Lake Dome. The volume change roughly 0.08 cubic kilometers of material intruding into the surrounding rock. For comparison, Mount St. 2004-2008 dome-building eruption involved 0.1 cubic kilometers of magma. Yellowstone's November intrusion was comparable in volume but occurred at greater depth and over a much shorter time. Three hypotheses competed to explain the data. Hypothesis 1. Basaltic magma from the deep reservoir, 20 to 50 kilometer depth, was intruding upward into the overlying rhyolitic magma chamber 8 to 16 kilometers, heating hydrothermal fluids at 4 to 6 kilometer depth, causing rapid pressurization and uplift. This scenario has precedent. It's the likely mechanism for the 2004-2009 uplift at Norris. Hypothesis 2. No new magma, but the existing magma chamber was degassing more vigorously, releasing volatiles that percolated upward, encountered impermeable rock layers, and pressurized. Hypothesis 3. The hydrothermal system's only deep circulation had changed due to tectonic fracturing, bringing hotter water into shallower reservoirs, creating pressure without magmatic involvement. Each hypothesis predicted different futures. The Yellowstone Volcano Observatory convened an urgent assessment on November 18th, using historical data from calderas worldwide, Long Valley, Campi Flagre, Rabaul, and Taupo. Scientists estimated probabilities for rapid uplift episodes of this magnitude and rate at calderas. Approximately 25 to 30% progressed to eruption within 6 months. Another 40 to 50% continued as unrest without eruption for months to years. The remaining 20 to 35% subsided within weeks. Applied to Yellowstone, roughly 25% chance of some form of eruption, likely hydrothermal explosion or small lava flow, not supereruption within 6 months, 50% chance of prolonged unrest without eruption, 25% chance the episode would end soon. These weren't predictions, they were statistical baselines from pattern matching. On November 19, 2024, the Yellowstone Volcano Observatory elevated the alert level from normal green to advisory yellow, the first change since the system's implementation for Yellowstone. The decision reflected 4 criteria. 1. Unprecedented deformation rate in instrumental record. 2. Sustained seismicity indicating active magma/fluid movement. 3. Increased gas emissions and thermal output. 4. Expanding deformation field suggesting ongoing intrusion. The alert level didn't mean the eruption was imminent. Advisory indicates volcano is exhibiting signs of elevated unrest above known background levels. But for Yellowstone, which receives 3 million annual visitors and sits near major population centers, even advisory triggered widespread attention. The National Park Service faced immediate operational challenges: close high-risk thermal areas where ground instability could cause injuries, continue normal operations with enhanced monitoring. The decision: close boardwalks within 2 kilometers of Mallard Lake Dome, increase ranger presence in thermal basins, install real-time seismometers and cameras at key locations, and prepare evacuation plans for the worst-case scenario, a hydrothermal explosion. These violent steam-driven eruptions occur when superheated water suddenly depressurizes, creating craters hundreds of meters across. Yellowstone's geologic record contains dozens of hydrothermal explosion craters. The most recent, 13,800 years ago at Mary Bay, leaving a 2.5-kilometer-wide depression. Within hours of the alert level change, Yellowstone trended globally on social media. News coverage ranged from measured NPR, Yellowstone shows elevated unrest, scientists monitoring closely, to sensational, tabloids, supervolcano waking up millions in danger. Misinformation spread rapidly. Fabricated evacuation orders, fake scientist quotes, conspiracy theories about government cover-ups. The YVO's website received 8 million hits in 48 hours, temporarily overwhelming servers. Scientists held daily briefings emphasizing 3 points. Elevated unrest does not mean imminent supereruption. 2. Most unrest episodes at calderas don't result in eruptions. 3. Monitoring continues 24/7 and the public will be informed of changes. Honesty about uncertainty was the strategy when certainty was impossible. Yellowstone's most dramatic historical uplift occurred at Norris Geyser Basin between 2004 and 2009, 18 centimeters total, at the time the fastest rate ever documented. Seismicity accompanied the deformation of thousands of earthquakes over 5 years, gas emissions increased, new fractures opened. Scientists intensively studied the episode, ultimately concluding it was hydrothermal, a pressurized aquifer beneath Norris, heated by the underlying magma chamber but not involving new magma intrusion. By 2010, the system depressurized and the ground began subsiding. No eruption occurred. The November 2024 episode at Mallard Lake followed a similar pattern, but compressed in time. What took 5 years at Norris was happening in weeks at Mallard Lake. Other calderas provide additional context. Long Valley, California experienced rapid uplift in 1980 and again in 1997 to 1998, 25 centimeters in months, accompanied by magnitude 6 earthquakes. No eruption followed. Campoflagre, Italy has risen over 3 meters since 1950 through episodic bradyseism, slow ground movement with acceleration phases causing alarm but no eruption yet. Rabaul, Papua New Guinea showed extreme uplift in 1983 to 1984 over 1 meter, then subsided without erupting, only to erupt a decade later in 1994 after a different precursor sequence. The lesson: unrest episodes are common, eruptions are rare, but not impossible. Each system is unique. Past behavior doesn't guarantee future outcomes. Modern volcano monitoring integrates data from multiple technologies, each capturing different aspects of volcanic processes. INSAR provides spatially comprehensive deformation maps updated every 6 to 12 days. GPS offers continuous three-dimensional position measurements at specific points with millimeter precision. Seismometers detect earthquake locations, magnitudes, and mechanisms, revealing subsurface fracturing and fluid movement. Tilt meters measure surface slope changes caused by pressure sources. Gas sensors quantify emissions of volcanic gases. Thermal cameras track heat flux changes. Each sensor type has strengths and limitations. INSAR sees the entire caldera but only every 12 days. GPS is continuous but only at station locations. Synthesis of all data streams provides the clearest picture. By late November 2024, the integrated picture showed 1. Continued uplift at a reduced rate, 5 centimeters per week compared to the initial 10 centimeters per week. 2. Seismicity plateauing around 30 earthquakes per day. 3. Gas emissions stabilizing at 250 tons SO2 per day. 4. Thermal anomalies persistent but not intensifying. The pattern suggested the intrusion was either stalling at a 6-kilometer depth or losing driving pressure. Neither resolution subsidence nor escalation eruption appeared imminent. The caldera had entered an ambiguous state that could persist indefinitely for weeks, months, or years, with elevated activity that didn't necessarily lead anywhere. In a novel approach, USGS scientists applied machine learning algorithms trained on global volcanic unrest datasets. The AI analyzed Yellowstone's November pattern deformation rate, seismicity, gas chemistry, spatial extent, and compared it to 847 documented unrest episodes at calderas worldwide, spanning 1980 to 2024. Pattern matching results: 62% similarity to episodes that subsided without eruption, 28% similarity to episodes that led to small eruptions, hydrothermal explosions, lava flows, 10% similarity to episodes preceding major eruptions. The algorithm couldn't predict Yellowstone's specific future, but it provided statistical context suggesting non-eruptive outcomes more likely than eruptive. The caveat: Yellowstone is unique in scale, fewer directly comparable systems exist in the training data. West Yellowstone, Montana, population 1,300, serves as a primary entry point to Yellowstone National Park. The town's economy depends almost entirely on tourism: hotels, restaurants, outfitters, and guides. When the advisory alert was announced on November 19th, the immediate effect was mixed. Some hotels reported cancellations 15 to 20% decline in bookings for the winter season. Others saw increased interest from volcano enthusiasts wanting to witness an active caldera. Net economic impact by late November, roughly neutral, but with significant variance between businesses. The psychological impact was harder to quantify. Residents who'd lived there for decades suddenly confronted the reality that the beautiful landscape surrounding them was geologically restless. Jackson, Wyoming, 70 kilometers south, faced different calculations: population 10,000, wealthier demographic, more economically diverse. Real estate agents fielded calls from concerned homeowners asking whether property values would decline. The answer, unclear. Volcanic risk had always existed but was abstract. The advisory alert made it concrete. Some residents began preparing emergency kits, reviewing evacuation routes, and purchasing supplies. Others dismissed the concern as overblown. The split reflected broader patterns in risk perception, those who'd experienced disasters personally or knew people who had prepared more seriously. Those whose lives had been disaster-free tended toward normalcy bias. Inside Yellowstone, tourists encountered a transformed experience. Closed boardwalks at popular thermal features, rangers provide safety briefings at visitor centers. More visible scientific equipment, seismometers, GPS receivers, and gas sampling stations. Some visitors found it thrilling to witness science in action at an active volcanic system. Others found it unsettling, cutting trips short. Park visitation in late November dropped 12% compared to the previous year, significant but not catastrophic. The National Park Service walked a tightrope, maintaining public safety without creating panic, keeping the park accessible while acknowledging real hazards. The December 2nd Sentinel-1 acquisition showed deformation slowing further, only 3 centimeters of additional uplift between November 20th and December 2nd. Cumulative uplift since late October, 35 centimeters over 1 foot, but the rate curve was flattening. GPS data confirmed the deceleration. By December 10th, daily displacement measurements were under 2 millimeters, approaching detection limits. Seismicity declined to 15 to 20 earthquakes per day. Gas emissions dropped to 180 tons of SO2 daily. The acute phase appeared to be stabilizing, though stabilizing didn't mean over or safe. The pressure source at 6 kilometers remained active. The intrusion hadn't withdrawn, it had simply stopped advancing. Scientists cautiously interpreted the pattern as intrusion stalling magma or fluids reaching a depth where buoyancy, temperature, or structural barriers prevented further ascent. The intrusion could crystallize over months to years, releasing heat gradually into hydrothermal systems without ever erupting, or it could resume ascent with minimal warning if conditions changed. Historical precedent from other calderas suggested stalled intrusions were common, but some stalled intrusions eventually resumed days, months, or years later. The satellite data described what happened, not what would happen next. Every 12 days, Sentinel-1 passes over Yellowstone, adding another data point to the time series. Every second, GPS receivers calculate their positions. Every earthquake is located and cataloged. The monitoring never stops. By mid-December 2024, Yellowstone remained at advisory status, elevated above baseline but not escalating toward imminent eruption. The YVO emphasized that the caldera could remain in this state for extended periods. Most unrest episodes at calderas last months to years without erupting, but vigilance remains essential because the small percentage that do erupt often provide limited additional warning before transitioning from unrest to eruption. Media coverage often leapt to super-eruption scenarios, the VEI-8 catastrophe that would bury states under ash and trigger global climate cooling. Scientists worked to correct this misperception. The November uplift, while significant, showed no characteristics of super-eruption preparation. Super-eruptions require mobilizing hundreds to thousands of cubic kilometers of eruptible magma. Geophysical imaging suggests Yellowstone's magma chamber is mostly solid, 85 to 95% crystals, 5 to 15% melt. Current estimates 200 to 600 cubic kilometers of potentially eruptible magma exists, but mobilizing that much would require extraordinary heat input and extended precursor activity, likely decades of escalating unrest, not weeks. The realistic eruption scenarios for November 2024's unrest were much smaller. Hydrothermal explosions, steam-driven, no magma, lava flows, low VI effusive eruptions, or localized phreatic events. Even these smaller eruptions would be significant hydrothermal explosions, could create craters hundreds of meters wide, and lava flows would necessitate evacuations and closures. But they're survivable, manageable events, not civilization-ending catastrophes. The probability of super-eruption in any given year, approximately 1 in 730,000 based on recurrence intervals. November's unrest didn't meaningfully change that baseline probability. Media narrative and scientific assessment diverged dramatically. Approximately 20 known supervolcano systems exist worldwide. All show periodic unrest. Most will never produce super-eruptions in human-relevant timescales, but smaller eruptions are geologically common, occurring every few hundred to a few thousand years at individual systems. Yellowstone has erupted at least 30 times in the past 640,000 years, since its last caldera-forming event, all smaller lava flows or hydrothermal explosions. This historical pattern suggests future activity will likely be similar: episodic unrest, occasional small eruptions, and extremely rare large eruptions. Living near calderas means accepting this reality, beautiful landscapes built by volcanic processes that occasionally reassert themselves. Satellites revealed that Yellowstone's ground rose 35 centimeters in 6 weeks, unprecedented in the instrumental record. The deformation indicated magma or hydrothermal fluids intruding at depth. Seismicity, gas emissions, and thermal changes supported this interpretation. By December, the intrusion appeared to have stalled, with deformation rates declining toward baseline. Whether this episode leads to an eruption, and if so, when and what magnitude, remains unknown. Most likely outcome based on historical patterns. The intrusion crystallizes without erupting, the caldera gradually returns to normal, and the episode joins the long record of Yellowstone's restless but non-eruptive behavior. But most likely isn't certain, and monitoring continues, because small probabilities of significant events still merit serious attention. From 600 kilometers above Earth, satellites watch the ground move centimeters that human eyes cannot see, patterns that reveal processes miles underground. Yellowstone rose 35 centimeters in autumn 2024. The mountain breathed deeper and faster than recorded before. Whether this breath was a sigh or the start of something more, only time will reveal. Scientists watch from orbit and ground, measuring every millimeter, every earthquake, every gas emission. They cannot control the caldera. They can only observe, interpret, and inform. And in that watching lies our best defense against forces older and more powerful than civilization itself.